In our current series of mini lectures, we have been focusing on the forces that shape terrestrial planets, and we've focused so far on cratering. We're now going to move on to tectonics. The word tectonics comes from the Greek word tekton, which means builder. Tectonics is the study of how structures on the surface of a planet are built and changed and destroyed over time, primarily by forces from the interior of the planet. So if we're going to study the surface and how the surface is deformed by the forces from inside a planet, we need to discuss how we can study the interiors of planets. You may already be familiar with how geologists study the interior of the Earth, but we'll go ahead and review that quickly before going on to discussing how we study the interiors of other terrestrial planets. So the way that we study the interior of the Earth and also of the Moon is using seismic waves. Earthquakes and moonquakes produce different kinds of waves. One wave is known as a P wave or a pressure wave, and this is also the way that sound works through Earth. Sound is a compression of the air. Pressure waves, P waves, work like this, and they can travel through liquids, they can travel through solids. You know this because you can hear things from underground or you can hear noises from outside your home. These waves come through rather easily. The other type of wave is the type of wave you may be more familiar with. That's an S wave. That's an up and down motion of the wave. And these types of waves do not travel through liquid. Now you may think, wait a second, I think this looks like ocean waves. Well, ocean waves, they're traveling on the top of the ocean. These waves do not travel through the ocean itself. The speed at which either a P wave or an S wave moves depends on the properties of the material it's moving through. And that can be both temperature and density and composition of the material. So by analyzing these pressure waves, these P waves, and the S waves, the up and down waves, we can study the density, temperature, or composition of material inside the Earth. So this is a complicated diagram. Don't get too worried about this. The primary thing is if you look at the picture on the upper left, you can see that P waves and S waves, they'll travel through the upper layers of the Earth, but the Earth has a liquid core. S waves cannot travel through liquid, while P waves can. So P waves can travel through a liquid, S waves cannot travel through a liquid. Therefore, there are parts of the Earth where you cannot see the S waves from an earthquake, and that's how we know that there's liquid inside of the Earth. And so from studying the waves like this, we've been able to determine the structure of the inside of the Earth, which we'll go through in a little more detail on the following slides. So here's one example, a real example. In 2013, there was a huge earthquake in Pakistan, a magnitude 7.7. You can see the red dot, which shows where the epicenter was, and the red and black circles are showing wave travel times, in fact, P wave travel times, to various parts of the Earth. In particular, if you look over at Japan, you notice that Japan is between the lines for 10 and 11. What that means is that seismometers in Japan should detect the earthquake 10 or 11 minutes after it happened in Pakistan. So let's see if that was true. The earthquake took place at 11:29 and 47 seconds Universal Time on September 24, 2013. And based on the arrival time, the estimated travel time to Japan, the wave should have arrived around 11:40 and 17 seconds. So let's take a look. Here's a seismograph from Hokkaido, Japan. And you notice that the seismograph is relatively steady until we get to about 11:40 and 17 seconds. And then you notice that it starts going all over the place. So therefore, the P waves arrived in Hokkaido, Japan, exactly at the time they were predicted. As I said, Earth's liquid core blocks S waves. In 2012, there was a strong earthquake in Canada, and in Antarctica, there are some research stations, and in particular, two of them are separated by about 25 miles. One of those stations, the S waves from the earthquake would have had to go through Earth's liquid core. And for the other one, it didn't have to go through Earth's liquid core. And if you look here at these two graphs, you can see that the graph on the left did not detect the S waves from the earthquake, while the graph on the right did detect the S waves from the earthquake. And so again, this shows you how even just a very small difference, a 25-mile difference, can make a huge difference in what the seismographs detect, and that's because of Earth's liquid core. Based on all of our studies of earthquakes on the Earth, here is the picture we have of the inside of the Earth. I do not expect you to memorize the sizes or the exact compositions of each of these parts of the Earth, but we'll just go through it briefly here. We believe that all the other terrestrial planets have similar parts to them, but the thicknesses of each layer can be very different. So the outermost part of the Earth we call the crust. That's the part that we live on. It's solid. It's made out of rocks. And it's only a few kilometers thick. It's a few kilometers thick in the ocean. It can be 30 to 50 kilometers thick on the continents. And the crust is made out of silicates, which just means lighter types of rocks with a lot of silicon in them. Sand is made out of silicon. Our computer chips are made out of silicon. Even things that seem like heavy rocks, like granite, contain a lot of silicon in them. Below the crust is the mantle. The mantle of the Earth is solid but deformable rock, so think like silly putty. It's definitely a solid, but it can flow under pressure. This plasticized rock, this putty-like rock, can flow but over very long time scales. And the mantle is quite thick. It's almost 3,000 kilometers thick. That's basically half the diameter of the Earth, not quite. And it is made out of silicate rocks like the crust, but that often have a little bit of metal in them, like iron or magnesium or nickel or other things. So they're slightly denser than the crustal rock. If we go deeper yet, we get to Earth's outer core. Earth's outer core is liquid and made primarily of metals. The most common metals are iron and nickel, but any other metal you can think of, copper, gold, tin, lots of those metals will be down in there too. You go further down yet at the center of the Earth, even though the temperature's getting hotter, you end up with a solid inner core, and it's solid because of the pressure of the overlying layers. And so this is the inner 1,200 kilometers of the Earth, and again, it's metals, iron, nickel, gold, silver, uranium, things like that. And these are dense elements. They're compressed to a solid at the very center of the Earth. So how did the Earth get this structure? Well, a couple of ways. Back when the solar system formed, if you think back to our chapters discussing the formation of the solar system, the Earth was made by a lot of rocky bits coming together, rocky things like asteroids. And the composition of these would have been well mixed. There would have been some metal, some iron, some nickel, other types of metal, some rocky type things like silicates or aluminum, and these would come together to make roughly a solid Earth. But as more and more meteors and more asteroids hit, that would release heat that would begin to melt the surface of the Earth. And on the inside of the Earth, there were lots of radioactive materials. And when radioactive materials decay, they release heat. Now, there were not a tremendous amount of radioactive materials inside the Earth, but there was enough, and the Earth is big enough that that little bit of heat that's released is retained. Rock acts like a very good insulator. If you could build a house with 3,000 mile thick rock walls, you could control the temperature inside very well. So the little bit of heat would build up and build up until the entire Earth melted. Once the entire Earth melted, the denser material would sink to the core. Denser materials would be metals, lead, tin, gold, iron, nickel, those things. Whereas lighter materials, which could be aluminum, which would be silicon, which would be other types of things that make up the rocks and the surface, would float upward. Eventually, the surface of the Earth solidified because it's exposed to the atmosphere and to space, where the temperatures are cooler and too cool for rock to remain liquid. And the interior of the Earth has been slowly cooling off ever since. Today we estimate that there are still radioactive decays going on inside the Earth, but that the amount of heat lost by the Earth through volcanoes and through other processes, only about half of that heat can be explained by ongoing radioactive decay. What that means is the inside of the Earth is slowly cooling off, and over long periods of time, billions of years, the interior of the Earth will become more solid, especially that liquid outer core. When I say that the planet is cooling, I mean the rocks of the planet. We're not talking here about the atmosphere, and this is an extraordinarily slow process. So now let's talk about the moon. We know about the interior of the moon because Apollo astronauts left seismographs there. The moon has a much thicker mantle than the Earth does. So on the Earth, the mantle is about half of the Earth's radius, but for the moon, it makes up the vast majority of moon's radius. And then there's an interior core that's about 300 kilometers thick. Also, the moon's crust is much thicker than the Earth's. The Earth's crust ranges between a few kilometers at the oceans to maybe a couple dozen kilometers on the continents, whereas on the moon, the crustal thickness ranges from 60 to 150 kilometers, so more than twice as thick as that on the Earth. Because the moon has a very small core, it doesn't have as high of a density of the Earth. The Earth's average density is about 5 grams per cubic centimeter. That's between that of rock and metal. The moon's average density is about 3 grams per cubic centimeter, which is basically the density of rock. Here is a graph of some different types of moonquakes detected by seismographs left behind on the moon by Apollo astronauts. The seismographs continued to send data back to Earth until the 1980s, when their power began to get low. They were nuclear powered. Over time, they weren't getting refueled, so they just lost energy and we had to turn them off. But there were several types of moonquakes. Deep moonquakes, shallow moonquakes. These are movements within the moon's mantle and crust, similar to earthquakes on the Earth. But mostly what they picked up were impacts from cratering, from meteors. And so you can see some examples of those on the right. The Earth and the Moon are so far the only terrestrial bodies which have had seismographs put on them. So for the other planets, Mercury, Venus, and Mars, we have to surmise their interiors in other ways. One way we can do this is by detailed studies of gravity. So if you put a spacecraft into orbit around a planet, its overall speeds and overall orbit will follow Kepler's laws, but details of its orbit, little wiggles, can be affected by things like mountains or even the structure of the interior of the planet. And so by very carefully analyzing the orbits of spacecraft, we can get a handle on what the interior of a planet looks like. Mercury, although it's much closer to the moon in size than it is to the Earth, it has a very large iron core. Remember, the mantle of the Earth makes up about half of the Earth's radius, whereas Mercury's iron core makes up 2/3 to 3/4 of its radius, with the outer part being mantle and crust. So Mercury has a lot more metal on it than the moon. Why is this so? We aren't certain. Mars has had several satellites in orbit around it, so we've been able to get a reasonable estimate of its interior. Not as precise as we could by seismographs, but Mars's interior seems to be similar to the Earth, just with a slightly thicker crust and thicker mantle. That there's likely a solid metal core, a liquid outer core, and then some sort of rocky mantle and thick rocky crust. We will know more about Mars beginning in about 2 years. In May of 2018, NASA will launch the Mars InSight mission, which will go to Mars, and it has two basic instruments. One is the seismograph. This will be the first ever seismograph on Mars, so we'll be able to look for Mars quakes as well as meteor impacts on Mars. And those Mars quakes will tell us a lot more about the interior of the planet. It will also be able to measure how much heat is coming out of the rock on the planet by having a drill that drills down very deep. This is similar to how we measure how much heat comes out of the Earth, and so we'll be able to tell how hot the interior of Mars is. Venus is even tougher to study. Venus is extraordinarily hot on its surface, and so we do not have the capability of putting seismographs on Venus. It's easy enough to send probes to Venus, but they can't survive for more than a few minutes on the surface of Venus, which means that a seismograph, which needs to sit for years to measure up plenty of Venus quakes, just cannot survive. So the measurements of Venus that we have are from orbiting satellites, and as far as we can tell, it looks very similar to the Earth. A metallic core, probably like the Earth, a solid inner core and liquid outer core, and a rocky mantle about the same size as the Earth's, with a thin crust on top of it. But we don't know the details. Here's our summary of the interiors of planets. We can use seismic waves on the Earth and the Moon, or we can use satellite measurements around all of the terrestrial bodies to deduce the interior structure of terrestrial planets. We understand the Earth the best. It has a solid iron core, and then a liquid outer metallic iron core, and then a mantle of this plasticized rock, of silly putty-like rock, and finally this thin crust on the surface. The Moon has a similar structure, but the mantle is much larger than the Earth's mantle, and its metallic core is very small, and we believe that the Moon is mostly solidified. As far as we can tell, Mars and Venus are similar to the Earth, and Mercury has a very large iron core compared to its size, and probably because Mercury is small, that iron core is mostly solid, but it might still be a little slushy in places. We don't know for certain.